Yeah, that's right. Well, I didn't make it. It was quite far off, so I looked at that as well. Fortunately, there was like a corner store, a spa, several elements.
Righto. Great pleasure to welcome Guofeng Zhang from Hong Kong. I asked Guofeng to give an introduction to quantum linear systems just because it parallels a lot of the classical control theory work. So there should be an element of familiarity here for control engineers. And Guofeng is also going to talk about some recent developments in this field where he's made a number of key contributions. Okay, Guofeng.
Thank you, John. Good morning, everyone. Name is Guofeng here from Hong Kong Polytechnic University. First, we look at the classical case, okay? For classical system, we start from a model, of course. Without the model, we can't do much. We start from model, maybe from physics principle, or maybe from some system identification, get this model first. This first thing we need to have when we study properties like stability, controllability, observability. For stability, maybe we have bounded input and bounded output. We can call it stable. Controllability means we have a system here. We plan to move to the other place. If controllable, we can move it from here to here within any short time. Arbitrary short time is okay. For observability, it's quite different. We have black box. We don't know what happened inside, but we have design input, output, and from input output data, we can restructure system precisely if it is observable, and no matter how short the data is. Okay? So we call it observable. This is a fundamental property of linear systems. We look at the system architecture, structure, common canonical decomposition, or co-prime factorization, something like this. Then we look at the response of system to input signals, for example, impulse, Dirac delta function, and step, like a Heaviside function for physicists, and sinusoidal, and maybe some other input, noise, something. This for system analysis. Then we move on to control, in particular feedback control, to get something we really need. Okay, so for linear system, classical linear system, we do all this actually. Okay. Now we move on to quantum system. First, I'll introduce the general linear quantum system, then move on to the particular one, particle systems. Okay, then talk about some application of the quantum linear system. Okay, the first example is very, very simple. It's just beam splitter, as just the two-byte matrix, two input, two output, and it's static, no dynamics involved. Right? The other one is optical cavity. The kappa is the coupling rate between in and out, between system and the input field. And omega is the frequency of the system, harmonic oscillator for this A. You have input and system operator and output here. Okay, this is particle system. Okay, the energy generation inside the system. Okay, and that one is the generic parametric amplifier (DPA). This one is a bit more complicated. Kappa is still the coupling parameter. Epsilon is a pump parameter inside the DPA. Okay, so we have A and A diagram, both of them. So we have this active device, not passive anymore, because it's not diagonal anymore. This one, you can see it's diagonal form if A and A diagram is diagonal form. But this one no longer diagonal. It's not a passive system. Okay. In general, for a linear system, I'm interested in is an oscillator. They have interaction among them, and driven by M canonical boson field. Okay, there are two parameters: n is number of oscillator, m is the number of channels. So here A is just a vector of A1 up to An, analysis of operators. Okay, for the system harmonic oscillator. A hash just some creation operators, and A dagger just pull this one down to make it a rule here, and this A brief just we have longer vector from A and A hash here, and A brief dagger just pull this one down. Okay, pull this one down. Okay, so there are notation I should introduce because I need to use this notation in the talk. Okay. Now I will use LTH language developed by John and Matt. Here in this paper. Okay, here S just a ML unitary matrix for a linear case, and L is a coupling operator in this form. Here C minus C plus are arbitrary MN matrices. H is Hamiltonian. Here omega is Hermitian matrix Cn by Cn. Okay, and this capital delta defined in this way as A B dagger this hash and A hash. Okay, so we have our parameter SLH given here. Then we can get our system. For beam tensor, just the S00, only the scattering matrix here. For optical cavity, we have just this S1. These are L, H is just the Hamiltonian of the system. For DPA, the system Hamiltonian is a bit more complicated. We have this term here. For closed system, just only for example, oscillator, just this omega A delta A. We have no input output, so this nothing here. Okay. Of course, we can use this language to describe nonlinear system. It's much more beyond linear case. Okay, even at H, we can write down the QSDE evaluation operator U and this one, and start from 0 for simplicity. 0 is identity operator, and by the two relations, we can get our linear system. Literal. Here, A, B, C, D are constant matrices. Here, this A, this C is given by this C, B is given by this form, and D just this form. Okay, so it's a linear system. This B brief is input. A brief is our phase system operator. B out is our output. Input and output relationship. Okay. Sorry, let's notation here. Gn is just some this commutation matrix here. In here. And sorry, this C brief. If C brief just some sorry, this should be brief here. The brief should be defined in this way. Okay. So we encode the system in 3 parameters. Write it in this form HC omega. They are all constant matrices here for the linear case. Okay. And now we have some fundamental relations for the linear system. These 3 relations here. The first one is from this commutation relation. So at all times, this should be preserved. Okay. So from this, we can derive the first fundamental relation here. And then from input-output, this output and the system operator are they commute. So we have from this we have this equation. And here this means D just symplectic. In our case, just the unitary because here as unitary, and the 0 here. So this one just a unitary matrix. Okay. More general, it can be a symplectic matrix. Okay. This was developed in this paper and also discussed in this paper. Okay. Then I move on to something very special, something I'm familiar with, or something I worked in. Otherwise, I can't talk confidently. Okay. But anyway, Yan gave a very good introduction to quantum linear systems on theoretical part. Okay, this paper. And Aliso Sarafini had another paper for experiment. And of course, one Melbourne have very excellent textbook, measurement feedback control. Okay, now we study three properties of system: stability, controllability, observability. Okay, here we average out. We take expectation of the system here. Then we can get get a classical linear system. So by taking average, everything becomes classical here. So classical linear system. For classical system, we can define stability, controllability, observability, right? So you say the quantum system is said to be curvy stable if the corresponding classical case is curvy stable. And controllable and observable, same thing here. This is the reference for the classical controllability, observability, something else in the book. Okay, this Keith Clark, professor at Cambridge. First result is given here. Here, G linear system is controllable if and only it's observable. If and only if this matrix have a 4-column rank. Okay, so we say for linear quantum system, controllability and observability are equivalent to each other. Okay, and this can be determined by this rank condition. Okay, actually, in 2005, Howard Wiseman and Andre Dahoty studied some problem. They established developability is equal to detectability for linear systems. Okay. Yeah, but it's true for more general case. Okay. The question is, it's still true in a nonlinear case or not? I looked at this problem last night, but didn't get the answer. Look, it's a bit tricky, but maybe not quite difficult, because here we have this A given this form, and B just minus C flat, and C this C. So this A had this had product of this C flat and C, same thing here. Okay, so you see this A had relation with its input and output matrices here. So maybe from here we can determine something about controllability or ability from nonlinear case by studying the relation between the input matrix, input coefficient, and output and the system coefficient. Yeah, probably it gives us something, but I'm not quite sure at the moment. Okay, but for linear, it's very clear. Yeah, I see here this matrix is very important because it gives us this property. Okay.
Sorry.
Yeah.
What does controllable mean?
Okay. We have a system which is located here at the moment.
Yeah.
Then we want to move it to somewhere else.
Yes.
And if controllable, we can do it within any short time. That is controllability.
Right. You can't go anywhere.
Anywhere within any short time.
But there will be states you cannot reach given your SLH.
You can reach any state.
Any state?
Yeah, if controllable.
Stays in the same state.
Average, yeah. Just this case, yeah. It's average.
Any state of the field?
No, any average.
Yeah, in average.
Averages of
Yeah.
Sure.
Otherwise, no.
That's
There's a
fine.
confusion of the word state between control theory and quantum
No,
mechanics.
fine.
Yeah. Okay.
Yeah.
Yeah, just this average classical dynamics.
Sorry
Okay.
for that.
And that's what we can define uncontrollable, unobservable subspace, which are given by this kernel spaces. Kernel of OS is unobservable subspace, and kernel of OSGN is uncontrollable subspace. The intersection will be the uncontrollable, unobservable subspace here. Okay, and it turns out that they have a special structure of this in this space. Okay, it can be constructed in this way. You see here, the V1 and here 0 here. And of course, I conjugate 0, a v1 here, and we have up a vl and l and 0 and vl hash. So you see, if we know v1 up to vl, we can get the basis of this space. So we can just focus on the upper part, v1 up to vl. We can get the whole space here. Okay. And then we can show that a matrix, a unitary matrix v1, v2, and such that the kernel, the v1, the union of v1, is an unobservable, uncontrollable subspace here. And v1, v satisfy this condition, okay? And v2 has the same structure as v1. Okay? Just it can be derived from Graham-Schmidt optimization condition procedure. Okay. And by this, we can get our decoherent free subspace here. Okay. If we know this range of v1 is invariant under the action of omega, Hamiltonian matrix, then we say if we apply this transformation v dagger to A, we can get two parts of the system. Part 1 is decoherent free subspace. It has no input and no output relation for this ADF. And this D means decoherence. It has driven by some, it's driven by some input and coupled some output here. We also have a decoherent free subspace decomposition based on this way, this structure. Okay. For final system, this problem is, was studied by many people. For example, Takazi, Viola, and recently Naoki studied this problem using Q quadrature form. But I found AIA diagram looks simpler than Q and P, so I developed a theory in this form. Okay. Okay, now we move on to something well known in classical control theory, transfer function. Just apply Laplace transform to input-output, can get the compact matrix denoted by G of S, which is our transfer function. It satisfies this relation. Okay. Now you can see this G flat looks like an inverse system of this G. However, we have to be careful. In most cases, this one is not a stable system. If you apply inverse Laplace transform to get the time domain function, probably it's not stable. Okay, so the inverse is not stable. So it may not be physical, but it's a useful property in many cases. Yeah, as a property. Okay. And then we define another matrix system sigma f in this way, relate it to the system G, like fractional form here. Okay, G sigma is given by this form. So you see the B is like this C flat and C is C. These are A here. It's very similar to our matrix OF. This C, this just the new A for sigma. Okay. So you see this OS just observability gramming for this sigma S. Okay, so you say if G is controllable observable, this one must be 2. Okay. Now we move on to a particular class of linear system called passive system. Passive will mean here C plus omega plus are both 0. Okay, now system can be in diagonal form. Okay, so we call it, now we have passive system here. We use only a annihilation operator to represent the system. Here A is in this form. Okay, we call this 1, 2 is a realization of the system, the transfer function G. Okay. And in transfer function form, G has this representation. In this way, a sigma should be in this form, and the relation still holds. Okay, the fractional form of G in terms of this sigma, okay? And then we have this equality for all omega. Now you can say it's just an all-part filter. For all frequency, the F value score is 1 here. So part system just an all-part filter in this way. For party system, we have stronger result. Not only controllability, stability is also, they are equivalent to stability. If a system is stable, must be observable, must be controllable for passive systems. Okay? These two are established by Martin and Naoki for passive systems. And also from 2 to 1, for observability to stability, also established by in this paper. Okay. So we call it controllable observable. It cannot have decoherent free subspace. It cannot have isolated element. So we say if system is stable, it cannot have isolated component. Otherwise, not Hurwitz stable, not controllable, not observable. Now you see for party system, it have very nice structure. Next we study some property of party system. First one is lossless bounded real. This defined by Yan and her student Eileen Malov in 2011. A linear party system is said to be lossless bounded real if Hurwitz is stable and equation 4, this equation hold. But this one naturally hold for all party systems. So we say if Hurwitz is stable, it's naturally lossless bounded real. Okay? And then we have lossless positive real, very well known property in classical control theory. So this cassette of S is said to be positive real if analytic in the strictly right half plane and satisfy this condition. Moreover, if this equality holds strictly, then we say it is lossless positive real. Okay? And then we have the following relationship between G and sigma. So G is lossless bounded real if and only if sigma is lossless positive real. Okay? But this theory has been developed in classical electrical networks many years ago. Actually, you can refer this book, very well known book. Okay? However, for the quantum case, the situation is more complicated. For example, this sigma is lossless positive real. You can check the conditions. However, by this construction, that G is not a physical system. It does not satisfy the commutation relations. It's not a physical system. The question is, what kind of sigma can give us a physically valid linear party system?
I just had a question about that. So when you're talking about a transfer function being physically realizable, normally, like you said, it doesn't satisfy the commutation relationships, but you'd have to find a realization of that transfer function.
Right.
So you're saying there's no state space realization of that transfer function which satisfies the commutation relations?
Yeah, I believe I get A, B, C from this G of S. I check the commutation relations, and they are not satisfied.
Right, but there's not a unique ABC for that G of S. There's a whole class of them. So
But unistry, so it should be fine.
what's that?
It's unistry transformation, right?
The transformation between the different ABCs.
Yeah, unistry, so it should be fine. But with party system, should be unit transformation between one to the other.
Right. Okay, maybe we can talk later, but I just remember looking at this example. I guess you put this on the archive, and thought there was something funny about it.
Yeah, because I think for this system, we can get ABC by applying unit for transformation, cannot use ABC. And this won't change community relations.
If you do a state-space transformation.
Yeah.
Well, it'll change the commutation matrix.
But overall, the commutator won't be changed. You have 2 per A, A and A dagger here, and U A dagger U right hand side, so we can put matrix out. Yeah, so I think it won't be changed. So that's why I think it's true for all realizations.
Okay, all right.
So I'll go back to this problem later.
Yeah.
Find some special sigma, which will give us a basically reliable quantum linear partitive state system. Before doing that, we move on to system structure, architecture. This system, this S is I, C minus omega minus this partitive system. It may have many channels, okay? Have this decomposition. Some channel will go swiftly away without any interaction with the system here. And some we have oscillator in this circle. Each one is a 1 degree freedom oscillator, just one mode, okay? And it have only one input, one output. Another one input, one output. But there are interaction among the oscillator, here, also here, okay? And we also have some other oscillator here. This one and this guy. This guy have no input, no output. No input, no output. Okay, but this one have no harmonic itself. This one has its own harmonic. So these two are a bit different. Okay, so if you cut this line, the system become uncontrollable and observable. So it's unstable. If you have this line, it's stable and controllable, observable. Okay. So we have a R input here, B1 up to BR, which drive our system oscillator here. Okay. Another representation is given here. Again, this set of B input will go away directly, without any interaction with the system. The other will have a bunch of oscillators. They are isolated from each other, no interaction among them. However, each of them is driven by several input, not only one, several input. Okay, and we have some other oscillator which have no input, no output. You can see if we cut line, it's a decoherent free subspace. Cut line or decoherent free subspace. Okay, so you see this related to controllability, observability, decomposition. Okay. Hunter Noddy and Ian Peterson proposed another kind of representation. We call it a cascaded representation, realization. You can see we have n modes. Each block is only one mode system, driven by input in this cascaded form. Okay, we call it a cascaded realization. And for the single input case, only one input channel, we have some other two representations. The first one we call it I call it a bus representation. Okay. We have principal mode. It's only one harmonic oscillator, driven by the input channel. And we have some other MS1 auxiliary oscillators, which are coupled to the principal mode by harmonic interaction. Okay, they have no interaction among them, so they are independent oscillators, except they couple to the principal mode. Okay, if you cut here or here, you get a decoherent free subspace. Okay, for this system, we have to get transfer function, which is in this form. Here, this part. This gamma over this part is just the principal mode driven by input. And this sum gives us the auxiliary modes here. Okay, because this is our fast representation. Another one is the chain mode representation. Here we have again principal mode. It is only one mode here, driven by the input channel. We have chain structure for the auxiliary modes here. Okay? If you cut here, you get a subspace which is coherent free, or you cut here somewhere, you can get other space. Okay? This idea is from physical chemistry community, for example, these two papers. These two, this guy and this one, did cut in this paper by John and me. Sorry, for this chain structure, we have this transfer function, this form. Again, you see here, this gamma bar over this guy is our principal mode. And the last one, this guy, is here, and come to the second last one in this way, and then all the way up, like conditional fraction form. Okay? Moreover, these two representations have some relations because they are from the same system, right? Okay, now we write the system in this way, this form. Because say this this guy have this form gamma over this one plus the sum, and this one also gamma over this guy over this one. So we write that sum in this way. It can either be the fast representation or the chain mode representation. Okay, so these two are related to each other in this way. Okay, and now if we define sigma s in this way, this delta is given by either of these two forms. And then we say this G must be physically a physical system because it's from our constructor. Yeah, so if we define this sigma in this either of these two ways, we can get a quantum linear partial system. Okay. Okay. Now I'll move on to some applications of the quantum linear system. This is a general architecture. We have planned P, this case controller to be designed. They may share some harmonic and P and K. This can also be designed with interacting harmonic. And the plan have input, the BV, maybe vacuum or maybe single photon or some other noise. Be in that W. W just some this may be a coherent input. This noise and this signal part of the laser laser beam or something. And the system have output, for example, this Y, which will be sent to the plant, to the controller. Then the controller will process Y and capture the output U and send to the plant P. We have feedback loop. Okay. And we have another variable Z. Here, this one may not be may not be a physical variable. Normally, we call it a performance variable. It gives us some criteria about the performance of the whole system. For example, if we have vacuum input, we want to study how the vacuum will affect our system. We'll look at this Z to see how what is the effect of on the system. Okay. Another example, if you have some coherent input, some disturbance, and from this Z we can see how it will affect the whole performance. So this is some called performance variable. Okay. And within this framework, we can study H-finity, FOG, and many other things within. Okay. This one paper by Hadi Mabuchi. Okay. The theory was developed in this paper by Matt Handler and Yan in 2008. We have this system is an optical cavity, a passive device, And it has output Y, which is sent to the controller, which is also an optical cavity here, and these are input to the system. Okay, and this W is just some disturbance, some laser input, something like that. Okay, it has finite some have energy. Okay, and this can be implemented in laboratories. I like this one. For LQG, it's more complicated because there are some studies, okay, but there are no analytic solution as yet. The problem is something like this. Okay, here, for example, for LQG, we have vacuum input. Okay, we want to suppress its influence on the system. We designed it K to get our control performance in some way. However, this K must be a physical, quantum physical system, right? We have to design some other part to get a physical system. So we have control part and some other part to guarantee physical reliability condition. But these two parts are entangled in some sense. You cannot separate them into two design procedures. Okay, in that way you can't get the analytic solution to this K. So this is much more complicated than the H infinity control. For this one, it's okay. You can get controllers parameter analytically. For LQG, as yet, still not possible. Next is about screening enhancement. We have a DPA, degenerator parametric amplifier. Now we add another channel, which represents the loss of the DPA. Okay, in our SH language, we have this S just the two-byte matrix, omega minus plus, and this C minus C plus. Okay, and the kappa is for this B1, and gamma is for this B2, which counts a lossy channel B2. Okay. Now we make a closed loop. Okay, this B1 and B1 out, and we pass it through a beam splitter. Okay, so we have closed loop here. This is studied. This was studied first by Yannick Saba and Kimura in 2003, and later by John and his student Widorfer. And this is implemented in laboratory in Furusawa's group. And recently, Mabuchi group used two OPO here as a controller to get a better squeezing from this guy to this guy. Here, squeezing means here we have this B, this input output here, and we get this. We can use the quadrature P and Q quadrature. We compare the output variance of the P and the variance of the input P is a ratio. The ratio we call the squeezing ratio. Okay, the smaller the better. I mean the better squeezing. Okay. And now we perform this study. We have DPA here. And now we have controller K here. This analytic operator AK, and some other input field to guarantee which one this is a physically reliable system. Okay, K has three parameters at K, L, K, HK. By some optimization procedure, we can get a parameter, all the parameter here, and then we compare our simulation with the existing ones. For this, remember gamma is a lossy, it denotes a lossy, and for this gamma, without any closed loop, only DPA itself, this guy, the squeezing ratio is 0.5. In the work by John and student, we got something like this. And with this controller, we can get 0.25, 0.26, something like this. Now, if we increase the lossy, it will be worse. Okay? But anyway, these two have similar squeezing ratio. Our program gave us this 0.33. It's a bit better than it too. However, our K is very complicated. For example, K can be represented in this way. We have here, L have LK1, LK2. HK has this Hamiltonian here. Have two input channels, one Hamiltonian here. So these are LK1, the first coupling operator. We have two mode squeezer here, which is dynamical system. LK2, two mode squeezer, dynamical system. These are system. This is DPA. There are three active devices to generate this K to get this squeezing ratio. Mabuch group proposed two of the OPO here for our K. They have some experiment to show squeezing enhancement. Now I move on to the last part of the talk, the single photon stuff. This is highly non-classical. Okay, we define some operator first. B, because it's just the time, some function of time. For example, this kind of function, norm 1. We define it B of Cathay this way, and B star is the creation. Okay, then we define our single photon input in this way. Okay, so this we call it a temporal power shift, temporal profile, or temporal power shift of the single photon. This just for demonstration. I don't think it's real, right? This kind of shape. But anyway, for single photon, input field traveling in the free space, and then we can get the mean value, which is 0. So if you average it, in average, no photon there, but it has non-linear correlation here. This one is from vacuum part. This one from the part. Okay, so you have an actual term for the correlation function in a single photon case. The problem is, given a linear system G, and given some photon input, single photon, multi-photon, what will be the output? One photon, two photon, or something else? For single photon, Matt and I derived the output power response analytically. This is the key formula in the paper. This is input power shift, say input. This is output power shift. And this is system transfer function. So from input output, we have very simple algebraic relations. Okay. And for the multi-photon case, it's much more complicated. The reason is the following. You have several input channels. Each channel may have several photons. So we need one index to count which channel it is. Another index to count which photon it is in the channel. And a third one to count which output channel we want to study. We need three index to count, to describe the phenomenon. In that way, we have tensor representation. So to study multi-photon signal processing, we have to use tensor computation. It's a natural mathematical framework to study this case. This problem addressed in recent paper. Okay, some demonstration here. We have a beam splitter here, and we have two inputs. Each one has a single photon, nu1, nu2. The output field will be in an entangled state. See here, two photons in the first channel, no photon second channel, and one photon first channel, one the other channel. This one with different shape, nu1 become nu2, nu2 become nu1. And here, no photon first channel, no photon second channel. We have four possible case situations, but this is a pure state here, entangled state actually. If we use a balanced beam splitter, 8 to 1/2, and nu1 equal nu2, I mean the two photons are indistinguishable, then we get a very simple form. Output two photons in the first channel, two photons or two photons in the second channel. just the Hong-Mando interference effect. Okay. Okay, now next one, again, two photon, two channel, but the two channels share a common power shape per side, T1, T2, not a product, a common power shape here. The two channels are entangled initially, two input channel, and we can get the output state 2 here, which is in this form. Okay, it's just what is derived in the book by Loudon. And okay, now you see, even the two input fields are entangled, we still can get our output state easily using our framework. This one is messy. We have two channels. Each channel have two photons here. Channel 1, two photons have Ct1, 1, Ct1, 2, two power shape. Channel 2, Ct2, 1, Ct2, 2, two power shape. And then output will be, we have 14 terms. Okay. Anyway, if we use binary beam transistor 1/2, and all photons have the same shape, they are indistinguishable. We have only 3 terms left. So 4 in the 1 channel, no photon second channel, or no photon first, 4 photon second, or 2 photon channel 1, 2 photon channel 2. Okay, so this is the same formula given by in this paper. Okay, now maybe we can ask this question. When photons are indistinguishable, the continuous variable version have the same phenomena as the discrete variable version. Maybe it's obvious in quantum optics, but I'm not sure. Maybe someone can tell me. If you do not distinguish your photon, these two give you same phenomena. I'm not sure, but it looks like the same thing. Yeah, because you see, for this study, Hong-Mando phenomena, they just count number of the photon. They don't study shapes. So I use the same shape, so I get the same equation. Yeah, for this one also, if we don't count the shape, because in this study, they only count the number. They don't care about the shapes. So they get this one. So I got this one too. So I think probably it's true, but I don't know, because I don't study, I don't know much about quantum, so experimental quantum optics. Okay, last one. We have a 2 channel. One channel here. The channel have 2 photons. They have a common power shape. The psi is just a Gaussian function, as though it's just the correlation ratio between the -1 and +1. Okay, we have pure state of 2 photons sharing a Gaussian temporal profile. Okay, now we pass it through an optical cavity, then get following structure. Here, rho is the parameter in this covariance matrix here. A correlation matrix here. Covariance matrix here. And this K, kappa is the decay rate of the cavity. You see here, this original input photon power shape, the Gaussian function. If K is small, the output power shape does not change much. But if it's bigger, it's much different from the original input power shape. However, but if it's K bigger enough, then we move this one to some other place, but keep the same shape, like transition from one place to the other place, but shape is not changed. Yeah, so something in between may be more interesting. So we have change of the probability, the shape here. Okay. By the way, here the cavity is empty, nothing inside initially. Yeah, recently, Matt and some other colleagues studied the quantum memory, a special one called gradient echo memory, GEM. They have a quantum linear model which is not a stable model. It's an oscillating model, but it's passive. In that way, they can store input information. Yeah, they have some simulation which is confirmed by the experimental results. So it's very, very interesting study. So that's why I want to mention this paper here. So let me conclude. So linear system, of course, appears simple. A linear map from in to output, constant A, B, C, D. Okay, yeah, that's why it's computationally tractable. When get everything analytically for most situations, not all. And but anyway, it can give us some very interesting things, like what I showed you already. Okay, so probably the first, perhaps the essential step in the study of general nonlinear theory. Okay, I'll stop here. Thank you.
Okay, thanks, Guofeng. So time for one or two questions.
You talked largely about passive systems, and by that I understood systems where the response function is time shift invariant.
Time shift invariant. Oh yeah, time invariant system. Yeah.
But many systems, for example, quantum memory, will often have a control signal which is not time shift invariant.
Right.
How does that alter the sorts of conclusions?
I'm not quite sure actually. But for the linear system, if the ABC, the coefficient, is time varying, probably it's still fine. Can still get the response, I think, because it won't change much. It won't change much, I think.
Maybe there would be certain mode matching issues in the case of an optical experiment.
If you talk about experiment, I can't say nothing actually. If I don't know experiment, I'm sorry. Yeah. From this formula, if you have time varying ABC, probably medicine will still be preserved. Yeah, but for experiment, model matching or something, I can't say nothing actually. Sorry. Yeah.
So I guess in those questions you looked about decoherence-free subspaces and controllability and observability, you could certainly define controllability and observability for time-varying linear systems, but I'm not sure if you'll get those same results that you got about the equivalence between controllability and observability, or the equivalence between stability and controllability and observability, in that if you allow things to be time-varying. Do you have any feeling about whether those same results would apply in the time-varying case?
The first question, Yin, is this. For classical linear system, for classical one, for example, okay, this one. If A, B, C, D are time varying,
Yeah.
I don't know how to, because I don't know how to study the controllability first.
Well, I mean,
It's first
standard
question.
systems theory ways of studying controllability and observability
So-
for time-varying systems, but I'm not sure whether these properties would hold in that case. Certainly for general linear systems, those 1 and 2 are not equivalent, and actually 3 is like a more complicated test for controllability in the time-varying case. So it'd be an interesting problem to look at.
So you won't have, you can't use rank condition to check controllability, observability in the time varying case.
There's a more complicated condition.
I don't study time varying
Yeah, if you look
systems.
in like a book on linear systems theory, there's like a more complicated rank condition.
Yeah, some transition matrix, some that
Well, it's
calculation.
obviously everything's a function of time.
Yeah. Yeah.
A question. I mean, this equivalence. Why? I mean, is there a symmetry? The old closeness?
It's a good
I mean,
question.
somehow more insight into. Can you give a little bit more insight why?
Yeah, because it's here, the parameter ABC, the B is here, C, they are C, right?
It's the same as C.
C is here, B is here, this B is C flat here, and C is here, right? So you see, A, B, C are highly correlated.
Yeah. If you go back, I think, to the previous slide. Oh, the next slide. The one. Yeah, that one. No, the one. The next one. That one. So you can see there's a relationship between B and C there.
Yeah.
That second one, which comes from the fact that the system variables commute with the output variables. So it's a physical property that systems variables have to commute with the output variables.
Right.
And that gives you that relationship between B and C. And once you have that relationship between B and C, then there's going to be a relationship between controllability and observability.
That's why I hope it is still true for the nonlinear case.
This is a physical property.
Yeah, that's right. Yeah, it's a physical property of commutativity. The system variables commute with the output variables. And then once you get that holds, then you've got this relationship.
The physical intuition I have for it is that it's any channel through which you input light into an optical cavity also has to be an output as well. That the coupling between the external degrees of freedom and the internal degrees of freedom is always going to be bidirectional. You can never have an input that only pushes things into the system. There's always going to be leakage out of that same input.
I think that's one of the fundamentals of quantum mechanics, really. That you can't.
Everything's
You can't. Yeah. Okay, that's another way of saying, can't get information out without pushing noise in.
Yeah, that's why I think that something similar may still be true for nonlinear case. We just have input-output relation, combination relations. Yeah. But I did some calculating last night to study, the such matrices.
Yeah.
But I can't get this structure exactly. Very similar, but a bit different.
Yeah. Maybe the linear but time varying case is like an easier case to study.
Yeah.
Because those, nonlinear things tend to be pretty hard, but linear and time varying things are a little bit harder than linear and time varying, but not that much harder.
So my guess is that at least the first two equivalent solutions still hold.
Yeah, pretty
One,
true.
need
Yeah.
modify for some time period.
Yeah. Because this true for all systems, this kind of relationship.
Yeah, in fact, I think these relationships
fundamental.
hold, if things were time varying, these would hold at every instant of time.
Yeah.
Also, just a slight technical thing is that middle line, the A should commute with the output field, where the T is now S, or S less than T.
T is big. When T is bigger than this guy, bigger than this guy.
Yeah, there's a causality.
Yeah. Like filtering problem.
Not just at that time.
Yeah. Of course.
That's important.
Like our filtering problem, that our filtering, that where we can build our filter, right?
Well, it's a structural feature.
Yeah.
So you need to have the out, or not just the data, but it's just the unnegate one as well.
Yeah.
Where the T is replaced by S, where S is less than T.
Just the input and G to output.
It's the local non-demolition condition.
Yeah. You can build a quantum filter from that combination when T greater than T. Yeah.
I'm not trying to talk about filtering. I'm just talking about a structural feature of the model.
Okay.
Should have the correct time values on the.
Yeah.
So it's different if you had a classical input Hamiltonian system. So they're conditioned on the system being Hamiltonian. Are these conditions the same or different actually? In the sense of Van der Schaaf or something like that, the linear system is Hamiltonian.
Classical.
Hamiltonian input-output.
So what's the
conditioning?
So maybe you should have the symplectic structure first.
Yeah, exactly.
Something the counterpart of this part. Then you can study.
Yeah, it should be very much analogous.
Should be analogous. Yeah.
I think that Port Hamiltonian system stuff with Van der Schaaf, it isn't quite the same as the quantum case. That I think they're sort of more general, so they wouldn't quite have that restriction in the second line,
Right.
Because they don't have the same form as the.
Commutation.
Yeah.
Yeah, one key difference is that the ports that they work with, there are no physical constraints about the ports.
Right.
There are physical constraints about the internal variables, but there's no requirement that there are inputs and outputs in the same physical sense as here.
Right. Yeah. So in a sense, probably you'd expect something like the first line to hold, because that's about the internal variables, but the second line is about the relationships between the inputs and outputs.
I didn't really understand this comment that you have an input also, every input channel also has to have an output channel, because the whole point of things like manipulating atoms, for example, via stimulated the Raman adiabatic passages is that you control a system by driving it with a laser without having any decay. Or all these techniques of controlling decoherence aims at you put something in that changes your dynamics without having anything coming out. Does that
What
fit
you're
into?
referring to is some kind of difference of time scales between different ports. Essentially,
For example,
you have some input, some ports which you rather use as input ports because they are actually much more weakly coupled than the other ports which you use as output ports. But in both cases, you have still a weak leakage out of that
Yeah,
weak
but you
port.
can, in the limiting case, you can get that to zero.
Exactly. Well, you can
So all these techniques are developed exactly to avoid this problem. That you can put things in, you can control, but without having any. Or if you have a decoherence-free subspace, you put your laser on, you go around in that subspace without having anything leaking off.
What you can't do in those cases, I think, is you can't put a single quanta of information in through those sorts of ports. Those are only
Why not?
Well, those are only ports that which you can manipulate terms in the Hamiltonian effectively. They're not terms that you can put in quantum information in through, as opposed to a photonic channel.
I can do a gate operation in a decoherence-free subspace.
But that's not added. That's not taking information from another quantum system and putting it into this one that's being driven.
So that's the.
Yeah. So the case where you have sort of say large lasers that are performing gates on an atom or something, I think of those as, like Maziar said, extremely weakly coupled gates through which quantum fluctuations can drive the system, but it's very, very weak. And so what you do to make it look to get a very how you make it useful though is that the signal that's doing the operation is a very, very large classical state, a very large coherent state that's doing the manipulation. The quantum fluctuations on top of that become negligible. You don't agree?
No, I think there are a lot of practical solutions, like for people do ion trap quantum computing, all kinds of things, and they need to fit in. Or my question is, do these kind of methods fit into your model, or is that a?
I don't know because I don't work on experiment. I don't know.
In this case, if the parameters in the dynamical model, the Hamiltonian and the decay terms, were controllable through some external classical control, that's where it would fit into here.
So that would in fact make these matrices functions of time, where those functions of time were controllable, right? But again, those things would still have to be satisfied at every time.
Right.
Okay, we've got this to close. Let's thank Guofeng again for the excellent talk.
Thank you.